Thank you. First of all, I will thank the possibility to be here. Thank the ASHRAE Hellenic chapter for this. Thank you for the possibility again. Well, start my work with supermarket for around 25 years ago, working with this energy modeling. So this is the topic. So it's very interesting for me to try to discuss with you my result and also some ideas, new ideas also related with energy utilization in supermarkets. So my presentation today, I will try first to have a short introduction about the supermarket and energy utilization there. After, about building energy modeling, I will have also some words about a project, Super Smart, that was a cooperation from different countries looking specific for supermarket. Some system and model for supermarket I use when I developed this program, CyberMark, that I will present as a fifth point. And after, we have a kind of discussion and conclusion. After probably, I will try to answer some of your questions. This is the idea with my presentation. So to start, about the introduction, now, during the last years, we have seen that the majority of the hypermarket and supermarket have increased in numbers. That means that the area of supermarket has also increased. So this is one part, and connecting with this, of course, we have more cabinet, refrigeration system, or the HVAC, and the requirement connected with this, about heating, cooling demand, lighting, whatever. The other factor that also influenced today the situation and the energy utilization in supermarket is new directive we have and regulation we have in EU to improve the efficiency in energy in different buildings, but also to reduce the emission of greenhouse gases. So these are the main topics we have today and the main challenge we have to solve when we are discussing energy utilization in supermarket. This is a picture showing that the increasing of number of hypermarket and supermarket in Europe. Here you can see different countries. You can see that in average, this is the amount of hypermarket and supermarket was around 44% in 2000, and today's, for 2011 is 62%. So it's a big change in this one. So this is one of the situation and also the factor that influence the area and also the system we have in supermarket. The other factor is this one, this energy performance directive related with the analysis energy billing. This one is not clear. It's each country that need to decide the definition of this analysis energy billing. I know that you have here, you have a decision about this analysis energy billing. In Sweden, we have, well, we start 2017, 2 years ago, more or less, using the value of 80 kilowatt hours square meter a year for buildings. It's not close to analysis energy billing. And this is, we start now also using the concept of primary energy. This is the first time we start using this primary energy concept there. So we start using this factor today is 1.6 for the electricity, and from 2021 we will start using the factor to 2.5. So this is the situation we have, and this of course will influence the situation about the energy for the building in We have this other one, this F-gas regulation. And this one, we have first the limitation of the use of these F-gases. And we know that in the majority of the supermarket today in Europe, and I suppose around the world, is R404A that we need to remove from supermarket. And this is the reason that today we are looking for other systems with CO2 or transcritical or some others, probably refrigerant, that can replace this one. We have also this banning of the use F-gases in different equipment, such as in cabinet, plug-in cabinet, for example. And we have also the prevention of the emission of F-gas. So all those factors, of course, influence the decision today about the system we use, about the refrigeration system, about the heating, cooling system, and HVAC, of course. If we look more specific for a supermarket and about the energy consumption, this is a picture for a project I was involved for some years ago, in which we studied supermarket from Sweden, from Canada, and from UK and US. And you can see here that the energy consumption in average for Sweden was from 350 to 450 kilowatt hours per meter in a year. In Canada was more or less double so much, in US around 600, and UK 800 to 1,000. And at the same time, we can see that if you look for the electricity use in supermarkets, we see that in US it's more or less 4% of the total of the national energy use for electricity. In UK, 3%, so it's more or less 3–4%. We look for France, Denmark, and also the situation we have in Sweden. From this project, from the Canadian and the US supermarket, here in this picture here, this blue dots here are 146 supermarkets from one supermarket chain in Sweden. This orange one is from some supermarket also in Sweden, but from other supermarket chain. This red one are from US, and this green one here, you can see, are from Canada. And in this picture, I use total energy divided by the total area of the supermarket, so it's kilowatt hours square meter a year. So this was one of the performance indicators we tried to study. But if you look for this one, for the conclusion, you say, well, the Canadian supermarkets are very bad if you look for the total energy. But when we start looking for the refrigeration system, or the amount of cabinet in total in the supermarket there, and we try to find another performance indicator in which we take into account the refrigeration capacity, we found that it was another picture. So we have, these are the US supermarket, and here you have a supermarket in Canada, so that's lower than the average we have in Sweden. So one of the conclusions about this project was it was very complicated to find energy performance indicator for supermarket, because you have so many factors that influence. If you look specific for what happened with if we share the energy in supermarket, we know that the refrigeration part is the main that is influencing the total energy. It depends, of course, of the supermarket. If you look for supermarket, hypermarket, probably this picture is, in this specific here is about 47–50%. In this hypermarket is around 35%, and if you look for the convenience, the supermarket is about 60%. So it depends, of course, on the area and how many cabinets you have, is that how much you use. This is another picture from some supermarket in US, and in this one the refrigeration part is about 40%, and you have the lighting, the cooling aspect. Another interesting factor that is necessary also to take into account when we discuss energy utilization in supermarket is if we look for the total cost structure and the profit of this one. If we look for this one, the product in a supermarket is around 76%. If we look for the energy, it's about 1% of the total cost. But if you look for profit here, it's around 3%. So when we compare energy, probably it's good that we compare with the profit and not with the total cost. It was also one of the conclusions. And it's also interesting to see that sometimes the incentive for the supermarket owner are probably also the energy, in some cases, are probably not the most important cost they have. There are other costs that are more relevant for them. So this is my introduction. So I'll try to present the different factors that influence the total energy in the supermarket. If we move now for the building energy simulation, well, we know that in many supermarkets we have installed heat recovery, we have installed floating condensing, energy efficient lighting, different efficient cabinet, system with CO2 as I mentioned. This is refrigerant CO2 as I mentioned with lower F-gas emission. But the supermarket branch has more or less used the trial and error approach to implement and evaluate new ideas and concepts. So probably we need to have another way to do that. This was the idea when I started with the project for many years ago, was to develop a model in which was possible to predict and evaluate the introduction of new concepts and ideas in supermarket. Of course, when you have a model, probably it's easy for you to evaluate which is the best solution, refrigeration system, HVAC, lighting, and evaluate, because it's an interaction between the different subsystems you have in a supermarket. So it's important to take into account all the factors. There are many models for evaluation of energy efficiency, renewable energy, and sustainability in buildings. If we look, I suppose you have that in the U.S. Department of Energy, there is information about different tools for wall building energy simulation. We have iPhone 67. Was last week. And if we look for this, the majority of those wall building energy simulation are able to model building and HVAC performance, but not the refrigeration system and not the interaction you have between the cabinet and the indoor conditions. So this is the main challenge when you try to model this one, is how you can see the relations you have between the cabinet and the indoor conditions. I will show more about this modeling, but my idea with this one was that we have many wall buildings energy simulation tools, but it's necessary something to find some specific. I will show some other from this supermarket project that we probably propose to check if you are looking for simulation for supermarket. This is the project Super Smart. This was it's a cooperation between 9 partners. Sintes, the coordinator from Norway, is Sheku. This is a company that help different companies to present the product. You have the National Research Council of Italy, the German Environment Agency, KTH, my university. We have this technical university in one of those from Germany. Circe, that is a company from Spain. And we have some company from the Republic of North Macedonia, and also from the IAR, this is the International Institute of Refrigeration. And the main idea with this one was first to identify market barriers. After was removing this market barrier through education, through presentation of information in different parts. The other one was an introduction of a new European eco-label for supermarket. So it's a proposal that was sent to the European Union for discussion of this European eco-label for supermarket. And also the main idea was also the reduction of environmental impact of supermarket. This was the main goals of this project. Here you have different reports that are possible. I know that I tried to, this homepage there, in which you can download all this report. This is connected with the International Institute of Refrigeration, and they have some problem with the homepage, so it was not possible to open this, but I hope that they will fix it soon. But here you can see that you have first this mapping of the barriers. The second one was a proposal for eco-friendly supermarket, overview, how to build a new eco-friendly supermarket with focus on carbon dioxide system. The refurbishment, another about computational tools for supermarket, another was about eco-friendly operation and maintenance of supermarket, and the last one about this eco-label. You have a lot of report in this homepage, you can download and see. From this computational tools for supermarket, I took from the list some of the most important tools. One is this Coolpack. I don't know if you have worked with this, but this is a collection of simulation program that you can use for designing, dimension, and optimize the refrigeration system. This is a freeware, so you can use it. We have another that is a cool tool. It's a software. I think this is a commercial software for planning and calculation of refrigeration and air conditioning system. And you have the other one, is Pack Calculation Pro, that is a simulation tool which comparison of the annual energy consumption of the refrigeration system. All of these three are the focuses only in refrigeration system. So you don't have the connection with the building in this one. It's only the refrigeration system. Other software is this Energy Plus, that is a wall building energy simulation. And this is a free, and is developed by the US Department of Energy. There are some third part that develop this interface. One of this is Design Builder, for example. And part of this, one of the program of this project, Annex 31, they developed some specific module for supermarket with direct expansion and indirect systems. I don't know if they have CO2 system, but it's possible to do. But the problem is you need to find a good interface. There is this Open Studio that you can use also for this one. But it's a complicated program. The other one is Francis. It's a commercial software, which is well known for simulation of building. In this software, you need to develop your own model. There are some groups, they develop, for example, models for CO2 system, for cabinet, that probably is possible to use, but it's not so easy. And the other software we put there was this CyberMart that I will present later today. Now at Cutting Edge, we start a new project. The name is Building State-of-the-Art Supermarket, Put Theory into Practice. Well, we have the project leader is Summer Zawalha, and we have a new PhD student, Sotirius. I think it is from Athens. So he is involved in this project. And the main idea there is to reduce at least 15% the annual energy saving compared to standard CO2 systems, at least 25% of annual energy saving compared with conventional systems, and this system is the most efficient and cost-effective that can be installed in Sweden today. So if we look for this one, this is a normal booster system. We have this traditional in Sweden today in new supermarket. And this is the proposal we have. So it's float evaporation, we have the air conditioning system, we have space heating and water heating. And cities have now a proposal using ejector. We have a meeting next week with the different partners in this project, and we will discuss with them the best possibility. We will install this system in 2 supermarkets in Sweden. So this is information about SuperSmart and this new project in KTH. Now we move to this system model for supermarkets. So when I start looking for this one, as I explained before, this is the supermarket system that we have here. So we have the building here, we have the indoor condition, and this is more or less the indoor condition or the design condition for the cabinet, 22 degrees and the relative humidity of 65%. We have people lighting equipment there, and we can see here also the connection between the cabinet and the influence of the cabinet, the cold air into the indoor part, and we have the influence also from the temperature and relative humidity in the cabinet. In this case, I use an indirect system. So in this case, this is the refrigeration system. We have a secondary refrigerant here, and we have another dry cooler on the roof, and we have heat recovery that we can use for heat, the air coming into the building. So this was the main idea I use in the model I developed. Here I have another more conceptual model. So we have the building envelope, the outer condition, the HVAC, the indoor climate, the influence you have from cabinet, and also the cool rooms and refrigeration system and heat recovery that you can use connected with your HVAC. So this was more or less the system I developed for this conceptual model. Well, in Sweden, for around 20 years ago, we moved for this system, that is traditional system that I suppose is in the majority of the supermarket here, with a rack of compressor for the low temperature level and another one from the medium temperature level. So this is we call this direct expansion, and this is the normal system installed in many supermarkets today. And in Sweden, we installed this system, we call partial indirect system. So we have a chiller, we have a secondary refrigerant. In the majority of the cases, it's propylene glycol. The temperature of this secondary refrigerant is -4, -8. So the evaporation temperature for the medium temperature level is around -12. And we have another loop here. We call this coolant fluid, and we have a dry cooler on the roof. And the main idea for this one was to reduce the refrigerant charge. So, for example, today it should be an idea probably to have, instead to have a chiller with 4048, to have propane, for example. So it's only to remove the chiller and put a new one. It's one of the possibilities we're also looking for probably in the future. In the low temperature level, it was difficult to find secondary refrigerants because we are talking about -30 degrees about. So it's difficult to find because the high density and the viscosity. So this was the main problem. And also the other is that fluid working at this temperature, they have problems with the corrosion. So this is the idea that in the low temperature level, in many of the supermarkets, we use refrigerant, that means is direct expansion, and we use well, indirect system in the condenser side. Well, as I mentioned before, this is the new system we install in many supermarkets, is booster system. So all the new supermarkets are moving to CO2 system. So this is the normal system today, at least in Sweden. I will say some word about the heat recovery system when we implement this one. This is the main idea. Is the same chiller and the temperature as I mentioned before to the cabinet, -8, -4. And we have temperature for 36, that is to the heat exchanger connected with the HVAC system. And after we have an auxiliary heating there, if the heat from the condenser is not enough to cover the heating demand in the system. When we start with the heat recovery system, there was a lot of problem we found with mix of fluid, with the sometimes with low heating from the refrigeration system. And we started looking for this condensing, floating condensing system. And from the condition we have in Sweden, we try to have a condensing temperature moving from 5 or 10 Celsius degrees to 40 Celsius degrees. And of course, we need to pay for all the heating we have in the building. And in this one, we try to study what happened with the coefficient of performance of the refrigeration system. So in this diagram, we have the coefficient of performance here. We have here different evaporation temperatures, and we have different condensing temperatures. So for a normal, completely indirect system, we have an evaporation temperature about -12, so we are here, and we have around 40 Celsius degrees, that's the condensing temperature. So we have CO2 about 2.3. So if now, instead to have this, if you have floating condensing, I mean, if we are in the winter when we have a low outer temperature, we can, with the same evaporation temperature, and if we say 10 Celsius degrees, the COP increased to a value higher than 6. And of course, for the same cooling demand, you will use a lot of the electricity you use for your compressor. So this was the main idea when we start looking and implement this floating condensing. We installed another system we call EcoPump, in which we combine the heat recovery and the floating condensing with very good results. And I will show you one example later. This is the model I use for the HVAC system. And in this, here is the supermarket, and here is the outdoor. We have the fans, we have a rotary heat exchanger that is normal, at least in Sweden. I don't know here, but we use this one as a way for heat recovery. We have also recirculation of air, and how much is the fresh air we put into the supermarket or into the building is depend of the carbon dioxide percentage we have in the building. So if you have many people there, you increase the amount of fresh air in this part. Here you have different coils. One is for air conditioning or cooling. You have the coil for heat recovery connected with the temperature I mentioned before. And here is the coil for the auxiliary heating, that in case the heat from the condenser is not enough to cover the heating demand. For the cabinet, we try to find a heat balance for this. So here are the different factors: the wall, the infiltration, radiation, lighting, the fans, and this heating wire. And we found a correlation between the temperature, the indoor temperature, and the percentage of refrigeration load. That is this one. So for a temperature of 25 Celsius degrees, indoor temperature, you have 100% the cooling demand for your cabinet. That is the design condition for your cabinet. And if you reduce this, of course, you reduce also how much is the percentage of this one. We develop also another model for this horizontal cabinet, and that we use more for the low temperature level. And we work with this one. Is another picture, but in this case, is the temperature here is lower for the temperature, the product you have there. So, I think now I will move for this, present this software I developed. I hope that you can see this. Well, this is a CyberMart, and here you can open a new file. And here you have well, the building part. And here you have the climate. You can select from different places here. I don't have a point there, but I have Stockholm, and I calculate here. So in this picture, you have here the temperature, the outer temperature, the relative humidity and the humidity ratio, and here is the solar radiation during 1 year. We have the building envelope. So here you can give the dimension of the building, length, width, the height, the total area, the safe area. Here you can see the different walls you have, and this is in the inside or outside, and this is because sometimes the supermarket are part of the shopping center, so these are you can select this. And which kind of, we work with 3 different kind of construction, heavy, medium, and light, and this is related, of course, with the insulation. We have windows there, which kind of windows you can select, and if you have window shield. The other one was related with the ventilation, and here you can select if you have recirculation of air and a rotary heat exchanger, or if you have only rotary heat exchanger or recirculation. You here decide how much is the efficiency of the rotary heat exchanger. Here is the volume flow, how much is the in cubic meter hour for when the supermarket is open and closed, and when you have winter and summer, and the pressure drop of your ventilation system. Here you can define the infiltration in the supermarket. Here we have the lighting, so you can define here how much is the lighting when the supermarket is open and closed. The equipment you have, here is how much is the service water. And here I developed a profile using how many people you put here, the maximum occupant a day. And here for Monday to Friday, so Sunday, you can decide, well, in Monday I have around 50%, and Saturday probably I have 100% of this occupancy. And here I have the daily profile, how many of these people are from 8 to 11 or from different times. Here is also a question about the plug-in cabinet. That's today is an important factor. That you have many, sometimes for some specific product, you have this plug-in cabinet. We, as I mentioned, are looking also for a possibility that instead to have centralized system, is to have plug-in cabinet with propane as a possibility. It's also probably in the future the possibility. Here you can select the opening hours, so when the supermarket is open and closed from Monday, Friday, Saturday. And here you can decide if you will have heat recovery or if you will have only we can say a constant condensing temperature. Here you can decide which are the indoor temperature, winter time and summer time. Here you select if you have district heating, oil boiler or electric boiler. air condition, if you have a chiller or district cooling, but in Sweden and in Stockholm we have district heating and district cooling. This is the reason I have this one. You have the price for the electricity and also the price for this. I have one Swedish krona, that is more or less one euro is 10 Swedish krona. So this is around 0.1 euro per kilowatt hour, the price of the electricity. Later you select the system. I will select this direct system here, 404A, reciprocating Bitzer compressor. Here you select the cabinet. For example, I have different cabinet that you can select here. And here I calculate how much is the refrigeration capacity for the medium temperature level and for the low temperature level. From this one, I move now for the calculation of the energy, and I calculate here you have how much is the electricity or the energy is for the heating, the heat recovery, the total heat, service water, the fans, the lighting, the equipment, and the total electricity I use here. I will compare this with a system with floating condensing, so we can see how much we can save when we use in the situation we have in Stockholm. So here I have the energy, and here I have the cost. I don't know if you can see here, but this is a reduction about 10,000 euro per year. Yes, this is, yes, more or less. So you have a reduction. You can improve the system only when you have, instead to have a constant condensing temperature and instead to have floating condensing. You can, I have a different refrigeration system, this completely indirect system, partially indirect system, that I evaluate this parallel system, and with subcooling I also evaluate with the supermarket. But here I have this CO2 transcritical that is not validated. So this is necessary to validate this model. So this was CyberMart. When I developed this software, we used this software to design a supermarket in Lambohov. So these are results from measurements for 1 year here. These are here, these measurements. And here are values for the CyberMart. Here we can see that it's a difference, 10%, 9% more or less. And we start to see what happened with why is the difference. Of course, you know that when you are working with modeling, you have always many factors that influence this one. The behavior is one. You don't know when the people open doors, when you have new product coming into the supermarket, increase the infiltration, change the temperature, influence the table condition, the variation you have from the heat recovery system, for example. But in this system, we use this echo pump. That means that you need to have a sensor to evaluate the outer temperature, and according to this one, you can decide how much is the condensing temperature, and also if you have floating condensing. But one of the results from this one was the temperature after this dry cooler was never lower than 20 Celsius degrees. So we started looking, and the sensor was placed indoor instead to have the outdoors. So this was the reason that we had, one of the reasons that we have the difference. So one of the conclusions also there is that it's necessary when you install new system, it's necessary to compare your theoretical values with the measurement you have. So for some conclusion now, there is a great potential for improvement of energy system in supermarket. We have a big challenge now, as I mentioned before, with all this new regulation, with all the new supermarket installed in many countries in Europe. The system model is necessary to predict and evaluate introduction of new concepts and ideas in supermarkets. A particular energy efficient solution for each supermarket is possible, but I think, and this is my opinion, it's necessary to find a balance between the energy performance, the cost, and it's not only the investment cost, it's also the energy cost, and of course the environmental impact, and this is related to the use of this F-gas. The implementation of new energy-saving technology requires an extensive analysis of energy performance. It's necessary to study this during a long period. It's not only 1 month or some days. You need to evaluate this during probably 1 year or 2 years. Today, when we install this CO2 system, we know that these are very sophisticated. You have many control systems. And of course, it's a challenge for the people working with the service and maintenance to have a control of all the subsystems connected with this, as the heat recovery, as if you have air conditioning. Because the main focus in supermarket is to maintain the appropriate temperature in the cabinet. This is the first goal. And of course, when you are working with maintenance and services, of course, your main focus is to have the appropriate temperature in the cabinet. It's not to have heat recovery or the air conditioning system. So, thank you very much again to be here.